Hello. Good evening. Um, Hello, Kumar sir. So, can you tell if my screen is visible?
Sir, good evening. Screen, no, sir. Presentation not visible.
Okay. Just a second. Now I think it should be visible, right?
Yeah, yes.
Okay. Okay. And my voice is audible now.
Oh, voice audible, sir. Yes.
Okay. Okay. So we'll just continue from the last class. So can I start? Like, six time? Can I start?
Yes.
Okay. Yeah. So we were saying this particular problem, right? So the gate parameters are given. In this problem, we had to find out what is the current rise time and voltage fall time. And by extension, we also had to find out what is di by dt and dv by dt. We saw that the device is turning on, right? So with that, first question was what is the peak gate current during turn on? So initially when the capacitor is kind of discharged, right? And when you just give the VCC voltage, so what would happen is the capacitor, since it is discharged, it acts like a short circuit, correct? So the equivalent circuit becomes something like this, just VCC and then RG, right? So the peak gate current is going to be VCC divided by RG. And if you have, let's say, a VEE, right? Like, let's say plus 15 and minus 5 volts, correct? So in that case, the peak gate current would be 15 minus of minus 5 or 20 minus of minus 5 divided by RG, right? So basically the voltage difference divided by RG, correct? We saw that this can be modeled as a RC circuit, first order RC network. We saw how the gate voltage is going to increase, right? So this was the first problem. I think this was pretty straightforward. So the next question was, what is the current rise time, right? When the current is rising from 0 to 100%, right? So what is the current rise time and what is the di by dt? Right. So this was question number B, and question number C was what is the voltage fall time, right? Voltage is falling from VDC to 0, and what is the dV by dt? So to answer this question, we had to kind of understand how the device turns on, right? So we took the case of a half bridge, right? So yeah, we took the case of a half bridge. We saw that initial condition was something like the entire current is flowing initially through the antiparallel diode of S1, right? And you're trying to turn on S2. So what happens is when you turn on S2, we saw that initially before you turned on S2, S2 was blocking the entire DC bus voltage or VDC, right? Entire VDC was appearing across S2. So when you had to turn on S2, we saw that initially S2 turns on in the saturation region, correct? We saw that S2 will turn on in the saturation region, right? The reason being that the drain source voltage is equal to VTC. Okay. So as the gate voltage increases, right? Since it is in saturation region, the current is given by GM into VGS minus VTH, right? So if we assume that gate voltage increases linearly, current also rises linearly. We will make that assumption for now. Okay. So I channel is a controlled current source, voltage controlled current source. As VGS increases, I channel increases. So then we saw that there would come a point at which this I channel has risen so much that it equals the inductor current, right? So initially, some current was initially zero current was flowing through S2, right? Let's say 20 amperes, entire 20 amperes was flowing through body diode. And what happened as you turned on S2, some of the current will be diverted through S2, right? And some of the current through the antiparallel diode. And at one point, what would happen is the gate voltage has increased so much that the entire current gets diverted through S2 now, right? So entire 20 amp will be carried out by S2 and this one doesn't carry any more current, right? So that is the point at which we saw that, okay, we have reached the load current. Now the voltage will start falling. So why didn't the voltage fall earlier? Because since this diode was conducting, you know that diode cannot conduct if there is a positive voltage between cathode to anode, right? So until the diode stops conducting, the voltage cannot change, right? It's just the basics of a diode, right? Yeah. So we saw that this is the reason. That's why S1 cannot block any voltage until the interpolate diode conducts. So after that, what happened? We saw that, okay, so once we use the load current, right? After that, your VDS starts to fall. Okay. We will again assume that the fall of VDS is quite linear, right? And you know that till this point, right, until VDS falls to a very low value, the device remains in the saturation region. Okay. So one more aspect we saw was that, okay, since now that the current has transferred entirely to S2, that is just not IL, right? There are two more aspects to it. One is obviously that, there is the antivalent diode that was conducting previously, right? Now antivalent diode stops conducting. So after all, it is just a diode, right? So diode would be having its reverse recovery. So as the diode current falls, you know that it will not directly go down to zero and stay at zero. It will be having a reverse recovery, right? So this reverse recovery corresponding to the reverse recovery QRR and the peak reverse recovery current, there would be a reverse recovery time. Right? So this reverse recovery current through the diode, if you can trace it back, you know that that current will also flow through S2, right? It completes its path through S2, correct? So that is why we see that after um, IDS reaches IL, there is a bump, right? This bump is contributed by IRR, the reverse recovery current. Also, so this is one component, that is IRR, right? One more component is that, okay, so if we tell that the voltage is changing, right? If we tell that the voltage across the device is changing, it means that effectively the voltage across the capacitances are changing, device capacitances, right? In our case, the output capacitance of the diode, output capacitance of the device. So we initially assumed that, okay, if it is going to be a charging current, the current would be in this direction, and if it is discharging or taking up the charges, the current will be going out, right? So we saw that since S2 is turning on, right? S2 is turning on, so the output capacitance has to discharge, and S1 is on. And so since the voltage across S2 changes, S1 voltage will also change correspondingly. Okay? So if S2 capacitance has to discharge, the easiest path is through the channel of the device S2. So you can see this dark green color, right? COSS2 discharges through the channel. So this will also add some extra current corresponding to COSS2 into dV by dt, right? Also, as S2 discharges, you know that S1 will charge proportionally. Why? Because the total DC bus voltage is constant, right? So total DC bus voltage is constant. So S2 discharges, S1 charges, right? So you know that S1 charging means a COSS one direction would be something like this, right? From top to bottom. So if you trace back the current path, you will know that it will come from VDC through COSS1, then through the channel of S2 and back. So you see that IDS2, right? The channel current of S2 is now made up of the load current, reverse recovery current, and COSS2 discharging current and COSS1 charging current. So we have three extra components over here, and that is what actually contributes to this overshoot, right? So we saw that this is something that's going to happen. Okay. So this is this mechanism. Next, what we tried was we tried to quantify this, right? So for how long this is going to happen, right? So we saw that initially it takes some time for the gate voltage to rise from VEE towards V threshold. Until it reaches V threshold, nothing is going to change, right? So this time is called turn on delay time, TD on, right? You gave the gate pulse from the microcontroller, you give high signal over here, but you see that the device will actually start carrying some amount of current only after it hits the threshold. So this is kind of the delay time before which the device responds. So this is called the turn on delay time. Okay. Next we have the current rise time, right? Wherein the current rises from zero towards the rated load current IL, right? And then we have the voltage fall time, wherein the device voltage falls from VDC to zero. Okay, so we have the three time periods now. We try to quantify the time periods. Okay, right. So what did we do to quantify this? We took the 8 of the gate side current, right? We tried to plot what would be the gate current, right? We tried to plot what would be the gate current. Okay. Okay. So initially, during TD on, we saw that, okay, so this is our TD on interval. I'm giving a high pulse at this point, right? So what would happen as I give the high pulse, then initially I'm going to get the IG peak. We saw it in the problem A itself, or the first problem itself, right? So I gave this yellow color, that is the high pulse over here. So what happened was you are going to get a peak gate current, right? And what would happen? This is an RC circuit. Initially, the capacitor is uncharged, right? And then what would happen is slowly the capacitor would go on charging, right? That is why your gate source voltage is increasing. CGS is getting charged up, right? So CGS is charging up, so your gate source voltage increases. If as your CGS increases, as your voltage across the gate source increases, you know that the charging current decreases, RC circuit, right? So initially the current will be high, then the current decays, right? That is why as gate voltage increases, gate current decreases. We will again assume that the fall is linear. You know that the fall is not linear, it's kind of exponential fall. But for easier purposes, practical purposes, we will assume it to be linear for now. Okay. So what you see is that, right, as VGS increases, IG decreases from IG peak towards, let's say, this is I1. So what is this point? I1 indicates the gate current at which your VGS hits the threshold, right? This is your turn on delay time. So during turn on delay time, your IG peak has decreased from IG peak to I1. So from this, we found out what is the expression for turn on delay time. Right? So, so how did we find out the expression? So one thing was, see, you know what is IGP, correct? IGP is basically VCC divided by RG, or VCC minus V divided by RG. I1 would be what? We do the gate circuit, right? This is just the gate side circuit. VCC is there, RG is there, and then you have the input capacitance, CISs. Across the input capacitance, you have your gate source voltage. As gate source voltage increases, the current decreases, right? So at VG is equal to 0, IG is the maximum. Then at VG is equal to V threshold, IG would be what? VCC minus V threshold divided by RG, correct? So this is I1, right? VCC minus V threshold divided by RG. This is your I1, right? This is your I1. Okay. So what we did was, in order to find out the actual value of the turn on time, we averaged out the current. You know that current actually changes from IGP to I1. So we averaged out the current. Right? That is, your average current would be this orange line, IGP plus I1 by 2. Right? This is the average current. I can also write that this gate current is the same current, right? The same gate current is flowing through this capacitance, right? This current can be written as C dV by dt, right? CISS into dVGS by dt, right? Just KVL equation, that is current through RG, we equated to current through CISS. So CISS into dVGS by dt. Okay. So your VGS is changing from VEE to V threshold, right? VEE to V threshold. So that is why your IG is CISS into V threshold by the time, C dV by dt. V threshold minus VEE divided by TD. This is the average gate current during turn on delay time. Okay. So equating this, right? Equating this, we found out what is TD on. But the question was to find out what is the rise time, right? TR. So what happens during TR? During the current rise time, your gate voltage increases from V threshold towards some point called VM, V Miller. We call this as the Miller voltage, right? Gate voltage increases from V threshold towards VM. So as gate voltage increases, obviously gate current will decrease. And initially it was at I1, right, at the beginning of this interval, right? And when VGS reaches VM, your gate current becomes I2. Okay, so gate voltage has fallen from I1 to I2. Again, we will find out the average gate current, right? That is average gate current. This yellow line would be I1 plus I2 by 2, right? I1 plus I2 by 2 would be the average gate current, right? So what is I1? I1 is corresponding to the gate current at threshold voltage. So I1 would be VCC minus VTH by RG, and I2 would be gate current corresponding to the Miller voltage at the end of the current rise time, right? So VCC minus VM by RG. Remember that in the question both V threshold and V Miller are provided. Okay. So this is the gate current I1 and I2, right? We will know what is I1, we know what is I2, right? Average gate current is this. So this average current is flowing through what? This average current is flowing through the input capacitance CISS, that is CdV by dt. So what is a dV over here? The voltage is changing from V threshold to V Miller, right? V threshold to V Miller. So the average gate current in terms of the capacitance is EISS into V Miller minus V threshold divided by the rise time TR. Okay. So what we did was we equated this current, right? We equated this current with the average I1 plus I2 by 2. So C dV by dt is I1 plus I2 by 2. Okay, we know what is I1, we know what is I2, right? And then from there we found out what is TR. This is the rise time, right? So we know all the parameters, CISS, we know what is V Miller, V threshold, RG, everything is given. So you know what is TR. Okay, if you know what is TR, you can always find out what is di by dt. So if you know what is TR, you can find out what is dV by dt. Di by dt is basically IL minus 0 divided by TR or IL by TR. So, Selokumar sir, like till this point, any doubt how we are computing all of this?
No, sir. It's clear.
And this is clear, right? How we got what is
Yeah,
TR.
yes, 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 sir.
So just equate C dV dt with the KVL equation.
Yeah,
And this.
yes.
Okay. So this was one part, right? That is question number B. What is the current rise time? Next part was how to find out the voltage fall time. Okay. So did we do voltage fall time or no? I don't know. Did we
Sir.
do voltage fall time? Sorry.
Oh, we find TR and TD and
Okay.
some.
So we did not do voltage fall time, right?
Yes.
Okay. Okay. I'll just start from here.
Sir, this final exam, these questions will be columns will be there.
I don't know actually because like whatever sample questions are provided, right? So they were all based on numeric. They were all based on theory only, right? You saw those
Okay.
problems, right? And they were all mostly very simple in terms of answering them. It's not that difficult. So
Okay.
I don't know to be exact because I am not part of the paper. So these questions are we also have courses in IT Delhi regarding the WBG devices. So with the aid of those courses and they are making these questions. Okay. But yeah, I think these are relevant to WBG device understanding, right?
Okay.
So So far, there is one assumption that we have been making. Okay. So the assumption is that so the assumption is that, right, if I have to draw the half bridge once again, right? Right. So we were talking about the turn on of S2, right? We were talking about the turn on of S2, and so far what we assumed was, right, the gate current is coming like this, correct? The gate current comes like this. Okay. So now you know that physically or in a practical device, CGS is much more than CDS, much more than CGD. Okay, right. And um, so what we saw was that initially during TD on and TR, right, your entire gate current IG, mostly flows via CGS, correct? Or you can also tell it is CISS. CISS is basically CGS parallel to CGD. Okay. The reason we were able to tell this was that during TD on and TR, you saw that VDS doesn't change, right? VDS doesn't change. That means that dVDS over dt is 0, correct? dVDS over dt is 0. Okay. So dVDS by dt is 0. But let me redraw this circuit over here. So Okay. So can you tell me what is the KVL equation of VGS? How will you write VGS in terms of VGD and VDS? How would you write what is VGS? So
VGD
you
plus
know that,
VDS.
correct. So basically your VGS can be written as VGD plus VDS, right? So if I differentiate it with respect to time, you know that dVGS over dt is equal to dVGD over dt plus dVDS over dt. Correct? So this is kind of the KVL equation from KVL equation. Correct? Now what we saw was that during your turn on delay time and TR, right, your dVDS by dt is 0, right? So during TD on and TR, right? Your voltage doesn't change. Voltage, drain source voltage doesn't change. It is VDS, VDC, right? It's 0. Why? This is because VDS remains at VDC. Okay. So dVDS by dt is 0. You know that, or we know that dVGS over dt is equal to dVGD over dt plus d VDS over dt, right? So dVDS over dt is 0. So dVGS over dt is the same as dVDS over dt, correct? Okay. So the rate of change of voltage across your gate source and drain source, I'm sorry, this is VGD. Right? So dVGS over dt is the same as dVGD over dt. So that is why what we tell is during your TD on and TR, during your delay time and rise time, right? You're having a circuit something like this in the gate side, right? It comes over here, right? And this is your device. So now it sees two parts. One is through this and one is through this, and obviously the current would be splitting in both directions. So your IG was coming over here, right? IG was coming over here. Some current will flow through this and some current will flow through this. Okay, so one is through, so this is your CGT and this is your CGS. Okay, so the current through your total IG, right? So your total IG that comes over here gets split into, yeah, so your total IG kind of gets split, right? So your total IG gets split into CGS dVGS by dt plus CGD dVGD over dt, right? We just saw that dVGS by dt and dVGT by dt are same, right? So we will substitute that over here. CGS dVGS over dt plus CGD dVGT by dt can be written as dVGS over dt. So CGS plus CGS plus CGD into dVGS over dt, right? Or this is your input capacitance, CISS into dVGS over dt. Do you understand this? Your gate current gets split into CGD and CGS, right? And you also know that dVDS by dt is 0 during the turn on delay time and the rise time. Okay, that's why your gate current gets split. And over here, you know that since the gate current is getting split and the dV by dt is same, you know that CGD and CGS are kind of in parallel, and that's your input capacitance. So this is during turn on delay time and rise time, right? So far we have seen this. Okay, so is this clear? Um, Selvakumar sir and Ravidas, is this clear?
Yes, sir.
Okay. So this was during your turn on delay time and rise time. Okay. But now in the next interval, right? The next interval, we saw that your voltage is falling, right? Your voltage is falling, something like this. So there is going to be a huge dV by dt during this particular interval. Okay. Huge dVds by dt. Huge dVds by dt. So you can no longer have this assumption, right? You can no longer have assumption that dVds by dt is 0, right? Because voltage is actually falling. So in the next interval, what you observe is during the voltage fall time, during TF, right? Or people write TVF, voltage fall time, right? So during this period, dVds by dt is very high. Okay. And you imagine, right? So when voltage fall time is going to start, right? Voltage fall time is starting at this interval 2, right? At the end of rise time. So what is the state at the end of rise time? When voltage fall starts, right? This is a point, right? Your gate current is I2, right? Gate current is I2. Your gate source voltage is Vm. Gate source voltage is Vm, right? Gate current is I2, gate source voltage is Vm, right? And your VDS was VDC. So let's just jot it down over here. So at the start of TVF, right? Initially, so the VDS VDP is very high at the start of the voltage period. Your Ig was equal to I2. What is I2? VCG minus Vm by Rg, right? And your VGS was equal to Vm, right? And your VDS was equal to VDC. Okay. Now we will go back to the diagram that we drew, right, over here. So let me redraw this. right? So if I tell dVds by dt is very high, right? So what is the dv by dt? So this is, so basically this is VDS, right? Drain to source, right? This is VDS. So if I tell the dVds by dt is very high, the voltage at this point, right? Voltage at the drain terminal with respect to the source terminal is falling too much. Okay. So now you imagine VDS. So let's say VDS is VDC is somewhere around 400 volts. Okay, VDC is around 400 volts. And what about your V Miller? V Miller is, I think, 9 volts or 9.5 volts. I forgot. 9.5. Yeah. So VM is 9.5 volts. VM is the same as VGS, right? And this is the same as VDS. Okay. So you tell me, right? Can I safely assume? Can I safely assume that DVDs, since your DVDs by DT is very high, yeah, and of course the voltage at this point is zero. Okay. So since DVDs by DT is very high, I can write that DVDs by DT is almost the same as dVdG by dt. Can I write like this? Or I can write huh, the dVds by dt is almost same as dVdG by dt your because your gate source voltage is very small, right? Compared to VDS. Because VGS is much less than VDS. So I can write that dVGS by dt, right, is much less than dVDS by dt. Is this fine? Ravidas and Selvakumar sir, I will write that um, I will write that since gate and source voltage is very small, right? So dVDS by dt is almost same as dVdG by dt. That is source and gate voltage is very small. So I can write dVDS by dt is almost same as dVdG by dt. Do you understand this?
Yes, sir.
Okay. So then what you would see is that since so let me draw this switch in a zoomed manner. Okay. So right. Mhm. Okay, I'll just take this to the next page. So as I was telling, right? So let me draw the um, gate source in a zoomed in manner. So you have your VCC gate resistance, and you have your Okay, so right. So your okay. So your gate, your drain voltage. So your device is turning on, right? S2 is turning on. So if S2 is turning on, what would happen to the drain source voltage? dVds by dt is positive or negative? Voltage is falling, right? dVds by dt should be then what? Right. So can you tell me what would be the um, polarity for dVds by dt? Should it be positive or negative?
Is positive.
See, if it is positive, it means that drain source voltage is increasing. Okay.
Oh,
So,
DVDs.
tell dVds by dt should be negative, right? Because the voltage is falling. It is turning on. The device is turning on. Correct? Do you understand? dVds by dt should be negative, right? Right? Because the voltage is falling from VDC to almost zero. Do you understand? So the dVd by dV by dt should be negative. The voltage is falling. Do you understand? Is this fine?
But
Uh-huh. Take your time to process, please. Do you understand this? The device is turning on, right? So from this also we see, right? That is over here. Yeah. See over here, the voltage is falling. dVds is falling from VDC to zero, right? So dVds by dt is negative, correct? Do you understand?
okay, after TR means after
Yeah, yeah,
L2, when
yeah. Now
VDS
we are
is below
dealing
0.
about the
Yes.
voltage fall time. Yes, right. So
Okay.
VDS will fall from VDC to zero, right? So now the
Yes.
point is, yeah. So now the point is, we saw in the previous slide that um, since dV by dt is very high, right? Your dV by dt is very high. So we saw that the gate source voltage is very miller, is nothing compared to VDC. So your drain dV by dVds by dt can be almost approximated as dVdG by dt, right? Correct. So then what you see is that one thing was, of course, we saw. So how does the CDS discharge? We are talking about the voltage fall time, right? So how does the CDS discharge? So voltage is falling at this node, right? The voltage between drain to source is falling like this, right? That means that the capacitances are discharging. How does CDS discharge? CDS was initially holding 400 volts. How does CDS discharge? What will be the path? So we saw that the capacitance discharging means if this is plus and minus, what would be the polarity of capacitance discharging current?
-2 plus.
Correct. Minus to plus. It would be flowing like this. So you see over here, CDS has to discharge, which means that the current has to flow from minus to plus, right? So it will come over here, right? it comes over here, the easiest path is through the channel because the channel is now turned on, right? So it will flow like this and come back, right? This is something we saw earlier also. So it will flow through the channel, right? So we saw, I think, yeah, I don't know in which slide it is. Yeah, here also we have seen it kind of flows from COSS2 to through the channel, correct? So over here, you understand that CDS will discharge through the channel itself, correct? CDS discharges through the channel. Okay, this is one. Selvakumar sir, are you understanding?
Yes, sir.
Okay, so this is one. The next thing is, you see at the drain terminal, there is a voltage. We saw that dVds by dt is almost same, right? Same as dV dg by dt, correct? So in such a scenario, yeah, dVds by dt is same as dV dg by dt. So there is also a current flow through the gate drain capacitance, right? There will also be a current through the gate drain capacitance. So let me indicate the polarities: plus, minus, plus, minus, and plus, minus. Okay. So there will also be a current through the gate drain capacitance. Do you understand? There will be a current through the gate drain capacitance. Why? Because there is a dV dt across the gate drain terminals, right? Because dVds by dt is same as dV dg by dt. If you tell that there is going to be dV by dt across a capacitance, there is going to be a current. So what will be the direction of that current? From gate to drain or drain to gate?
Will be gate to drain.
It will be gate to
Gate
drain.
to drain.
Why are you telling that it will be from gate to drain?
Because this uh, VGD and VGS.
Hmm. Correct, you're right, you're right. So the point is dVds by dt is very high, right? Or dVds by dt is same as dVdg by dt.
G by dt.
So yes, so dVdg by dt is kind of negative, correct? That means that you are actually, as he told, again you are taking away charge from the capacitance, correct? So that is why the current should be something like this. It will come from VCC and it will go like this. Do you understand? It will go through the channel and then it will come back. Is this clear?
Yes, sir.
Again, it will flow through the channel only. Okay. So earlier what we saw that in this scenario, right? Till during the current rise time and turn on delay time, the gate current is splitting into CGS and CGD. And you know that most of the current would be flowing through CGS, right? Most of the current will be flowing through CGS. Why? Because CGS is very high than CGD, right? So this component would be much higher. This component would be very high compared to this component. Do you understand? CGS is much higher than CGD. CGS is more than CGD. Therefore, CGS into dVGS by dt is more than CGD into dVGS by dt. Do you agree? Do you agree with this? Till during the current rise time,
Yes.
most of the gate current will be flowing through CGS. Some current, small current will be flowing through CGD, but most of the current will be through CGS. Okay. But now what is happening during the voltage fall time? almost all of your current will be flowing through CGD only. So nothing flows through CGS. If nothing flows through CGS, you will see that the gate source voltage is obviously going to remain same, right? So your gate source voltage, um, let me take blue. So your gate source voltage will remain at V Miller, okay? Because no current is flowing through CGS, okay? No current is flowing through CGS, okay? Yeah, no current is flowing through CGS, right? No current flows through CGS. Entire current flows through CGD. So your gate source voltage doesn't change at all, right? This is your VGS. So your gate source voltage doesn't change. Do you understand? It will remain at V Miller. So VGS of T remains at Vm during the voltage period. Okay, is this fine? Do you understand this, both of you?
Yes, sir. Yes. Yes.
Okay. So that is why we tell that the gate source voltage is remaining at V Miller. And what about your current? Current was having this bump corresponding to IRR and the COSS current, correct? And your VDS was falling from VDC to 0. Okay, it became almost 0 at this point. So this is your voltage fall period until it goes to 0. So one thing is that right. So this is your IL. But what happens to your current? It will be having a bump. This bump corresponds to IRR, and there will be a constant current until this period ends, right? So there will be a constant current above IL. Why is this current coming? What is this current? Do you understand what I am telling over here? What is this extra current in IDS? We saw this.
Is it leakage current?
No, no. See, what is happening during the voltage fall period? During voltage fall period, basically, I don't know where is that figure by. So during voltage fall period, the capacitances are discharging and charging up. So the capacitance charging current and discharging current flows through the channel, right? We have drawn this in earlier class itself, right? So extra current is made up of what? IL, IRR, and CdV by dt for S2 and CdV by dt for S1. Okay, so this is the extra current. Even after IRR ends, see, IRR will end after the reverse recovery period, right? So IRR will end after the reverse recovery period. For the rest of the period, what are you going to get? There will be a component of ICOSS1 plus ICOSS2. Are you understanding this?
Okay.
Okay, Selvakumar sir, are you understanding this?
Yes, sir. Hello.
Oh,
Yes, sir.
yeah. So, okay, so now our point is how to find out the voltage fall period, right? So I think finding out the voltage fall period during this interval is the easiest. Why? Because your VGS doesn't change at all. Okay, VGS is remaining constant. And you see that um, your entire gate current is flowing through CGD. Nothing flows through CGS, right? So how do you find out the equations, defining equations? So one equation is C dV by dt. Over here, what happened, man? Yeah, so one equation is over here, Ig is equal to CGD into dVGD by dt, right? This is one. And the second equation is Ig is equal to VCC minus VGS by RG. So can you tell me what will be the relevant values? What will be VGD? So what is dV by dt? What is dVGD by dt? So dVGD is changing from what to what?
It's equal to TVDS by dt. No?
Correct. So it is equal to dVds by dt, right? So dVds is changing from where to where?
TVDS is
VD falling from VDC to 0,
yes,
right?
correct.
And what is VGS in the second equation? VGS is constant, right?
Correct.
VGS is constant at V Miller, right?
VGS equal to
So
VM. Yes.
VM. So directly we can find out. In earlier case and all, what we had to do was we averaged it out, right? You can see this orange line. We averaged it out, right? I1, I2 and all. But now we need not do that at all. It's very easy because directly we are having the equations. Okay. So during DVF, right? dVds by dt is almost equal to d VDG by dt, right? And it is falling from VDC to 0 divided by VF, right? And your VGS of P remains fixed at Vm or V Miller. So just equate it, okay? So VCC minus Vm by Rg is equal to C dV by dt. See, the value of capacitance is CGD, okay? CGD into VDC by TVF, okay? So TVF is equal to CGD into VDC into RG divided by VCC minus VM. Is this fine? Simple, right? Straightforward.
Yes, sir.
Okay, fine. So, okay. So let's assume that the voltage fall is linear. Okay, that is dV by dt is constant. Okay, dVdG by dt is constant. So since dV by dt is constant, right? So C dV by dt is constant. So the gate current is constant, right? Do you understand? This is a constant value, right? Because on the right hand side, you see CGD into VDC by TVF. If I assume that dV by dt is constant, then C dV by dt is also constant. On the right hand side also, VCC is constant. We just saw that the gate source voltage doesn't change. So VM is also constant and RG is constant. So the gate current is also constant. Okay. So that is why you will see that gate current also doesn't change during this interval. Okay, during this interval, gate current also doesn't change. Gate current remains at I2. Okay, gate current remains at I2. Okay, so can you tell me what is the answer for this? If you have calculator, you can just calculate. I think CGD was 19 picofarad, right? CGD, what is CGD? Yeah, 19 picofarad. So 19 pico into VDC was, forgot what is VDC.
400.
VDC was 625 volts.
625.
VCC was 20 minus VM was 9.5. Okay, so you will get what is TVF. Fine. Please tell me if you do this. I will also do. I am getting around 14.7 nanoseconds.
Correct.
Okay. Yeah. So now you have found out TVF. They have asked what is dV by dt. So dV by dt is VDC by TVF. So 625 by 14.7 nano, right? 625 by 14. So around 42.5 volts per nanoseconds, or people tell it in kilovolts per microsecond. Kilovolts per microsecond. Okay. So do you understand this? How we have done this? Ravidas and Selvakumar sir. So do you need me to recapitulate once, like starting from the after what happens in current rise? Till current rise, I think it is clear. So after that, should I summarize once or is it fine? Should I summarize once?
It's fine, sir.
It is fine. Ravidas, is it fine or should I summarize once? Okay. Okay. So your voltage falls and it has fallen to a value very close to zero, right? So after the voltage falls to a value very close. Okay. So one more thing is, let me write over here. During TVF, your VGS remains at VM. So your IG will be CGD, right? Or we can write CGD as CRSS. CRSS into dV by dt. So into VDC by VF. Okay. So since, see, you observe that during the first two intervals, TD on and TR, see, ISS is coming into play, input capacitance. But during the voltage fall period, the CRSS or the reverse transfer capacitance is coming into play. Okay. So Reverse transfer capacitance is also known as Miller capacitance. Okay. So CRSS is known as Miller capacitance. That is why the voltage fall interval is also known as Miller interval. The gate voltage during this period is called Miller voltage, VM, Miller voltage. Okay. Okay. So just note that the capacitances are different. It's not always the CGS capacitance or CISS capacitance. During voltage fall, it is CRSS. Okay. Fine. Right. So we saw that once the current rise time ends, right? Once the current rise time ends, then your voltages are going to change, which means that the voltage across S2 is going to fall and voltage across S1 is going to rise. If we tell like that, it means that voltage changes means the capacitance voltage is changing. Okay, so just remember the convention for what is charging and discharging, right? And you will see that the entire charging and discharging current flows through the channel of S2, right? And one more thing is, if you apply KVL, right? If you apply KVL in the device, you will see that the gate source voltage VGS is equal to VGD plus VDS. So dVGS by dt is dVGD by dt plus dVDS by dt. Okay. During the current price period and the turn on delay time, the VDS does not change. It remains at VDC. That is why we tell that dVDS by dt is almost equal to 0. So dVGS by dt is same as dVGD by dt. Okay. So the gate current gets split into CGS and CGD, and predominantly it will flow through CGS only, right? So this is during the turn on delay time and current rise time. But during your voltage fall period, right, there is a huge dVDS by dt. So compared to your gate source voltage, your drain source voltage is very high, or compared to dVGS by dt, dVDS by dt is very high. So dVGS by dt is almost zero, right? So dVDS by dt is almost same as dVDG by dt. Okay, because, and that is why we tell that during that period gate source voltage remains constant at Miller voltage. VGS is almost same as VM. VGS is same as VM, right? dVDS by dt is same as dVDG by dt. Okay. So then what we did was we traced back the current. So if there is dVdG by dt, then there has to be a current through the Miller capacitance or CGD. Okay. So that current direction is shown over here from VCC to RG to CGD. Earlier, the current was flowing from VCC to RG mostly through CGS. Now it will flow from VCC, RG through CGD. Okay. Right. So VGS remains constant. So your gate current in terms of capacitance is CGD into dVGD by dt. And in terms of your KVL, IG is VCC minus VGS by RG. VGS remains at VM, right? We assume that the voltage fall is linear. And since your dVDS by dt is same as dVGT by dt, your dVGD by dt is changing from VDC to 0, right, during TF. So substituting that, we found out what is the expression for voltage fall period. Okay. So you see it's a very high dV by dt, 42 volts per nanoseconds is quite high. Okay. So this is during the voltage fall period. So we have quantified what is current rise period and voltage fall period. So once we have quantified what this is, we have to find out the last part of the problem. That is find out the switching energy, right? We saw in the earlier class itself, see, as indicated over here, there is a overlap between the current and voltage during this period, right? Current is also non-zero and voltage is also non-zero, right? So we have to minimize this as much as possible. Okay, only then the switching energy will be lesser. We won't have less switching energy. Okay, so next is to find out what is this switching energy by finding out the area between these two curves. So I'll just start off with that. Uh, please give me around 5 or 7 minutes break. Actually, I'm not well, so I'll just drink some warm water. My throat is not good. But any doubt till this point?
No, sir. Okay,
Okay. I'll just start off. Then just give me 5 or 7 minutes break.
okay, sir.
We will find out
Sir,
what is the switching energy.
any new session you are going to start, sir?
Any new?
Are you going to start any new session or no?
Any
Today
new session means?
means now we have seen all switching characteristics there fall time, rise time, all no. Next,
Correct.
any new thing you are going to start or the same? Actually, I'm not
Uh,
feeling well now, so that's why
oh, okay,
I'm
okay.
asking.
Actually, I'm also not feeling well. I'm having some throat infection and cold. That's
Yes,
why my
same,
voice is also
same,
not
sir.
good.
That's why my voice is
Okay,
down.
okay. So
Uh,
just this switching energy alone, we will find out. Okay, I think that gives us the motivation to find out the switching losses. So we will find out the switching energy and close for the day. And from next class, I'm planning to start heat sink.
okay,
Okay,
sir.
heat sink
Thank
design,
you.
I think you saw in one of your previous lectures. So the idea was from here you will find out the switching laws. With the switching laws determined, and you will also know the conduction laws, right? That is I RMS square into R, I square R. So you will know what is the power loss in each device. If you know what is the power loss in each device, how will you find out the heat sink, or how will you choose a heat sink? Whether you need liquid cooling or air cooling. If you need air cooling, what is the heat sink specification that you should choose? I thought we will take some practical examples, right? We will find out the once we know what is the loss, we will find out how to determine the heat sink requirement. So that is one thing that I thought we should do. Next was you also studied about the crosstalk, right?
Yes, sir.
In one of your So we will see, right? I will just like how we have found out the dV by dt over here. I will give you the dV by dt, right? Let's say that for some application I need a very high dV by dt. Okay, then how will I find out my value of the required value of Rg or required value of negative voltage so that the device does not false trigger? Okay, that
Okay,
will
sir.
be based
Okay,
on crosstalk. So
okay,
those
sir.
are
Okay.
questions we will see from the next week. Today we will just one part is remaining, that is the switching energy. I will teach that and then we will close for the day. Okay, from next class we'll start
Okay,
heat.
okay, sir.
Okay, just give me 5 minutes time. I will just have some warm water and come back. Hi, sir. Can we continue now? Hello? Hello? Can we continue now? Kumar, sir, are you there? Can we continue now? Hello? Kumar, sir, am I audible? Hello? Hello, Kumar, sir, are you there?
Yes,
Can we
sir.
continue?
I am available.
Okay, okay. So the last part was the switching energy. So this part is pretty simple now that we have found out what are all the parameters. So I'll just jot down the parameters. Sorry, this is question number E, switching energy. So so far we have seen three intervals, right? That is TD on, TR, and TDF. So we should be worried about what? We should be worried about which intervals?
Sir, I'm not good.
Yeah, so we should be worried about which interval regarding losses. Should it be about the turn on delay time?
Turn on, turn on and turn off. Both the time it will be lost.
No, should it be the current rise time, voltage fall time, or turn on delay time? Which time?
It will be turn on delay time. Loss.
Turn on delay time should we be worried about during turn on delay time? We
No,
should be
no.
worried about
This the that time
during
also it will be
this
less, but
period.
TR will be high.
Yes, so we
The
should be
voltage
worried
fall
about the
down.
correct. So we should be worried about TR and TBF, right? Current rise time and voltage fall time. Okay, so we have found out all the values, right? So can you tell me what is the value for current rise time TIR? Uh, do you have that ready or should I calculate?
Let us see my old notes.
Yeah, please. Voltage fall time was 14.7 nanoseconds. PIR, you can just tell, and VDC, right? It was 625 volts, and
35.
the current IL was 20 amperes. No worries, if you don't have, we can just compute. So TR was CISS into VM minus VTH into 2RG divided by 2 VCC minus VTH plus VM, right? So what is CISS? CISS is 571 pico. Hmm. 571 pico. 71. 9.5 minus 3. Into 15. Divided by 3 means VTH plus VM. Around 3.5 nanoseconds, right?
Not.
Huh?
Not actually. I'm searching my notes.
Oh, then no worries. I calculated. I think it is 3.51 nanoseconds. That is what I'm getting.
Okay, sir.
Okay. 3509 pico. So 3.5 nanoseconds, right? So 3.5 nanoseconds is the current rise time. Okay. So for simplicity, let's right now forget about that reverse recovery and COSS current and all. Just assume that current increases from 0 to 20, voltage falls from 625 to 0. Okay. So how would your current look like? IDS, let's say this is till this point it was 0. It increases from 0 to IL and then remains constant. Okay. And what about your voltage? VDS remains at VDC till this point, and then it will fall to
Fall
0,
down. 0.
right? Okay. So okay. So this is IL, this is VDC, this is 0, and this is 0. So let's mark what is your power. Okay, instantaneous power loss. Okay, so this is P. So I will write P of T, right? Instantaneously is VDS of T into IDS of T. This is the instantaneous power loss, and this happens in the junction, right? Obviously, when voltage and current are overlapping, there is power loss. Happens in the junction of the device. Okay. So initially, it is 0 into VDC, so it is 0 during the delay time, right? So remember that this is your TD on, this is current rise time, and this is voltage fall time, right? So it is initially 0. Okay, it is initially 0, and then during this VDS is constant, IDS is increasing. So the net can be drawn as something like this. Is this fine? Net can be drawn as something like this, VDS into IDS, right? So over here, IDS is increasing from 0 to IL. VDS is constant. So the net is increasing, correct? It is like square into a triangle. It is what? It is just a triangle, right?
Yes, yes, yes.
And next is what? Next is your current is constant and voltage is falling. So the net is falling,
Fall,
right?
fall, fall.
Okay. And then it remains 0. Okay. Fine. So what will be this value? The peak value?
Value VDC and IL.
Peak value. Correct. So directly it is VDC into IL, right? You know the interval, you know the peak value. So this is nothing but a triangle, right? You have, you know what is half into base into height. Just compute this, you will get what is the power loss, right? So your P of T or okay. So okay, so your power is this. Then what will be the energy? So power is V into I. What is your energy?
Into time.
Energy is into time, or I can write this as integral P dt, right? Integral P
Yes.
of T dt, right? So I want to find out the energy. Okay. So I can write energy during the on period is basically integral T on, right? So integral P of T dt during the current trace period and integral P of T dt during the voltage fall period. Okay. So P of T is basically V into I, right? So I can write this is just area, right? Integration is basically area, correct? So integration is basically area under this curve, right? So what is the area? Instead of integrating this directly, we can find out the area, right? So the area is going to be half into
VDC.
VDCIL into height, right? Into base. So we have two triangles, one during TR and one during TVF. So I can write TR plus TVF. Is this fine?
Yes.
Right? Just these two triangles. Okay. This is the energy that is lost in the device when the device is turning on. Okay. Okay. So now that we know the values, just we will substitute and find out. So into so this is in nano or 1 3 something. So I'm getting somewhere around 113.75 microjoules. Is this fine? Are you getting the same thing? So
10.7.
yeah, so this is correct, right? So this is the energy that is lost in the device when the device is turning on. Okay. Okay, so this is the energy that's lost during this period. So now this was during the turn on, right? So now let's say a similar loss happens during turn off. Okay, so energy lost during the on period is 113.75 microjoules. Okay, let's say the energy lost when the device turns off, it will be generally lesser. Okay, so let's take some arbitrary value. Let me tell it is for simplicity, right? So let me tell that uh, yeah, so let me tell that this is 36.25 microjoules when the device turns off. Okay, so how will you find out this energy? You should again find out what is the, so when the device is turning off, current will fall, current will fall, and voltage will rise. Correct? The device starts blocking voltage. I am not going into that, it is the complementary. Okay, generally the energy will be lesser during that period because Rg during the off period is less than Rg during the on period. Okay, so total energy will be this plus this, which is 150 microjoules, right? So this is the total energy expended by the device every time it turns on and turns off. Okay, so this is the energy in microjoules. Therefore, average power will be what? Energy by time, or energy into frequency, switching frequency. If let's say switching frequency is 10 kilohertz, right? So the power lost, right? Power loss will be 150 micro into 10 kilohertz. How much is this?
1,500. Sorry, 1,500
Sorry, 1000 milliwatt or 1 watt, right?
milliwatt.
Or 1 watt. So
1.5
1
watt.
watt of,
1.5 watt.
oh sorry,
Yes.
1.5. So this is called as the switching loss. Okay.
Okay.
So you understand that this much energy, right? This much energy gets expended every time when the device turns on and turns off. When the device turns on, this much energy is gone. When the device turns off, this much energy is needed. So total energy is this much, and this will every time. So when will this energy happen? This energy loss will happen every time the device turns on and turns off. That is corresponding to the switching frequency. So if you are having a switching frequency of 10 kilohertz, the power loss will be 1.5 watt per device, right? So if let's say I make switching frequency from 10 kilohertz to 100 kilohertz, then what will happen to the power loss? It will become 150
15
micro
watts.
into 100 K, 15 watts. So
Yes.
your switching loss increases as power as switching frequency increases. Okay, that's why the switching
Okay.
loss forms a major component for WBG devices, because in WBG devices you go for higher frequencies. So
Higher
if you go to
switching.
high frequencies, there will be higher loss, higher switching loss. So you have to work towards how to minimize the switching loss, how to minimize the switching loss. And the way to minimize switching loss is minimize the times, minimize the current rise time, minimize the voltage fault time during turn on, and similarly during turn off, minimize the current fault time and voltage rise time. Okay.
Okay. Okay.
So yeah, I think this one particular problem itself took us like around 2-3 classes. But are you able to understand the concept?
Yes, sir.
Is this
I understood this.
okay?
Yes,
So
sir.
this is just voltage and current we have taken. But as I was telling the previously, the current will be having reverse recovery also. So in this problem they have not given, but if they give what is the reverse recovery, they will give what is QRR, right? So energy is what? Energy is basically QRR into voltage, right? That will be the energy. So what you will do is you will add in the turn on energy, you will add this plus, I'm sorry. So in the turn on energy, you will add plus the reverse recovery component, QRR into
You
voltage.
are.
Okay, right? Or there are multiple ways of doing this. Instead of QRR into voltage, you can also write it as this is just energy, right? So if you know IRR and TRR, right? From that, correct. So QRR into voltage. What is QRR? QRR is basically IRR into TRR. We have studied, right, how to find out
Yes, sir.
what is reverse recovery loss. So that component also will be added. Okay, but anyway, it's not part of the question, so we will not worry about that. So reverse recovery also happens every time the device switches. So that also needs to be taken into account. Okay. So yeah, so this was the entire problem. What is we are just summarizing it. Or we saw what is the peak gate current, right? Then what is the current rise time and di by dt? What is the voltage fall time, dv by dt? And finally, what is the energy loss?
Energy loss.
Okay, we did this for turn on. We did this for turn on. If you are actually designing a circuit, you have to do a similar analysis for turn off also, right? During turn
Okay.
off, you will see that during turn off, you will see that first the voltage will rise, okay, and then your current will fall. You understand now? It's just the opposite of this.
Okay.
First voltage will rise and then the current will fall. Again, it is because of the antiparallel diode. The diode will only conduct only if there is no voltage across it. So first the voltage has to change, then only it will start conducting current. You understand now?
Yes, sir. Yes.
Like I don't know where is the picture. Yeah. So first the voltage, this S2 has to start blocking the entire voltage. So the voltage across this will decrease. Only after that current will start flowing through the diode. So that is why we tell that during turn off, first the voltage increases and then current. Okay. So this is during turn off. Is this fine, cell phone method?
Yes, sir. Yes, it's fine. I'll try
Okay.
to find out that turn off.
Yeah, you can do that. So we
Yes.
can conclude over here. Okay. So if you have
Okay.
any doubts, just ask, or else we will conclude today.
No, sir.
From next class, we
No.
will go to heatsink.
Okay, sir. Okay.
Okay. Okay. Senukmar sir. Take care and
Thank
bye
you.
bye.
Thanks. Actually, today my throat pain, not able to speak loudly. But
Yeah, same. I was not able to talk at all.
thank you so much. Good night.
Good night.